So in the last 3 tutorials, we looked at how to build a reference library, plot it, and then edit it all in the web application. And now we're going to go on to do quantitative analysis in the full pattern summation tab. And the example we're going to go through can be, the data for it can be downloaded as RockJock Mix 1, which is a synthetic mixture that relates to the RockJock library. And we can also download the RockJock library. Instead of using the small reference library we've been working with so far, this one contains about 170 standards. So it's pretty comprehensive and ideal for geological and soil samples. And it was originally part of the RockJock software created by Dennis Ebel. So let's just load those two data files. This is XY format, and then this is our data format. So they're all loaded in. And the next stage is to select the solver routine used for the fitting process. So at the moment, I'm just going to keep those as they are. BFGS and RWP are ones that I use pretty much all the time and seem to give the best results. Now the next part of the process is to select the phases to use in the fitting. Now the application automatically selects the first from the list, which can be a little annoying. So I'm just going to delete that and then replace it with corundum. Now, let's just start with corundum, which is going to be the only phase used in the fitting process, because I know that this RockJock sample was prepared with 20% corundum, and chances are if you are preparing your samples with an internal standard, you'd know what it is and what concentration it's in. So because we've only selected corundum as the phase to use in the fitting, it's the only phase that we can select as the internal standard. And there's a box here next to it that allows you to specify what the concentration is. So let's tick that and say that it's 20%. Now there are further parameters down here. The first is the alignment parameter, which can be slid up and down. And this is a way of defining how much your measurement can shift positively or negatively by in order to optimize its alignment to the internal standard, which here is corundum. So if we set that to 0.1 for now, which seems to be the default, we also have a grid search parameter, which is an additional alignment protocol where the standard patterns are shifted by various amounts within a specified range that you've defined here in order to optimize the fit. We'll leave that at 0 for now. Next is the 2θ range to apply the full pattern summation to, which will use the full thing. Next is a slider that you can use to omit any phases that are quantified to be present in low concentrations. So if you set it at 0.05, if there are any phases below that percentage, they'll be removed from the analysis. We'll set that to 0 as well. And the last thing is the wavelength, and that's purely for plotting and calculating d-spacings on the plot. So we've loaded the data and set all the parameters up. Now if we click Start Computation, annoyingly it won't really show you what it's doing, but if you've done anything wrong, you'll know about it, because chances are the application might crash. But here we have the output. The first part of the output is the tabulated data, tabulated concentrations table, and then the bottom part is a fit. So we have a measured pattern in black, so double clicking on that isolates it. And then we have the fitted pattern, which is not really going to match this measure pattern because we've only supplied corundum to the fit. And the corundum pattern, pure pattern, obviously matches the fitted pattern because it's the only component. So if we zoom in on a part of the pattern on one of the peaks, we can see that the alignment isn't very good at all. So I would be tempted to increase this parameter to maybe 0.3 or so and recompute, because this is a really important part of the fitting process to make sure your alignment is correct. So that's recomputed now, and if we zoom in on that, you can see the alignment is pretty much bang on now, so I'd be happy with that. So that's got the alignment sorted at least, and now we need to add other phases into the mix in order to try and model this sample more accurately. Now, let's say we know what phases are in this sample. So I know that there's microcline, because these are synthetically prepared mixtures. There's illite, which is a 1M, sorry, RM30. There's a kaolinite, this one. There is no quartz. There's a labradorite and a smectite, which is the calcium montmorillonite. So I know that these are in there. I know that's not a very realistic scenario, but just for the sake of this example, we'll add all of these phases in and recompute. Again, we'll keep corundum as the internal standard, and the alignment and stuff all the same. So we'll recompute that, and the more phases you add, the slower it becomes. Still, it's relatively quick because we're only dealing with a few samples here. So now we have the measured and the fitted patterns more closely recreate. So the fit is more closely related to the measured now. We're explaining most of the variation across the full 2 theta range. And if you zoom in, you can look at various features, and so that's a pretty good fit for the sake of this example. In addition to this example, it's worth pointing out that since we defined the concentration of corundum, in the table we find up here, the concentrations of the various components are calculated taking into account the internal standard concentration. And so you'll find that corundum isn't present in the final output, but the phase concentrations are computed to account for that. But when you look at the plot, the corundum is still a component of the fit, and that's very important. Alternatively, we could say that we don't know the internal standard concentration, in which case the package will compute the phase concentrations by assuming that they sum to 100%. So if we do that computation, again, it will probably take a few seconds to run and plot. Now we see that corundum is part of the output, and we will certainly have the same fit. It's just the fact that these phase concentrations have been computed in a different way. Now, an alternative way of doing workflow of using this full pattern summation tab, particularly if you're not sure what phases you might have in a sample, are to choose in this solver selection box. If you choose non-negative least squares, you'll see that when in the select phases part, now you're only actually able to select an internal standard. And you can only select one, obviously. So I'm going to stick with corundum as the internal standard. And the reason you can only select this is because when you select non-negative least squares in this web application, it will use the full library. And it can do this because non-negative least squares is a really fast alternative to minimizing an objective function. So if we just recompute that now, we'll see what happens. So non-negative least squares, as I said, is pretty fast, so shouldn't have any problems with speed. And what it does is it compares the measured pattern to everything in your reference library. And if in your reference library you've got all the appropriate standards, it should be able to recreate the pattern very well. So here we actually have a very good fit now of the observed, the measured, and the fitted, particularly with this low angle peak here, which wasn't quite as well resolved in the fit we did earlier. And if we look at the table, we can sort them by percent, and we can see that there's quite a lot of phases that are quite low, present in quite low concentrations, and these distinct few that are present in notable concentrations. And what you can then do is use this plot to identify what phases are contributing strongly to your observed pattern. So quite obviously this calcium montmorillonite is contributing to the observed pattern, whereas dolomite, this blue line down here, it's probably being selected in error, which is which sometimes happens with the non-negative least squares algorithm. Nonetheless, though, it's a good way of finding out whether you've got enough data within your reference library to recreate the pattern and select phases from it. So if we look at the illite, for example, we'll see that that's another strong component. Obviously, corundum is a key component. We know that's in there, and so on. So that's a nice way of being able to then go, all right, now I know what phases I can expect. I'll move back to the BFGS algorithm and add the phases that are identified in the plot. And the last key component I want to outline in this tab is that you can use data that are measured on different instruments. For example, if the XY file you provide was measured on a different instrument to the library, it will automatically harmonize things, and it'll do that by calculating the overlapping 2 theta range and the and it will then interpolate to the coarsest resolution out of the two. So you don't need to really worry. It should all be pretty seamless when using data from different instruments, as long as they're measured using the same X-ray wavelength. And then if we go, once we're happy with the fit, if we go down to the bottom here, we can download the powdR FPS object as an R data file. So if we just save that, we'll come on to use it later. And that's pretty much it for the full pattern, like manual full pattern summation for quantitative analysis. And in the next tutorial, we'll look at how an automated approach can be used.